Welcome back, everyone. In this video, we're going to continue looking at work and energy, and specifically, we'll be looking at different types of forces. So, some things that we'll be trying to figure out in this video: what's the difference between a conservative and non-conservative force? And how do we use gravitational potential energy for situations involving vertical motion? What is elastic potential energy? And why do we call potential energy energy due to position instead of just calling it stored energy? So we're going to start with different types of forces. And the first type is the conservative force. So when we have a conservative force, the work in moving an object is what we call path independent, which means that as long as we begin at point A and end at point B, that the amount of work done doesn't matter on the path that we take, whether we go like that, or if we go like this, or if we have some other crazy winding path. As long as we start at A and end at B, we have the same amount of work done. Also, the work done in a closed path is equal to 0. So if we start at A and go to B and come back to A, the work is 0. And this is a mathematical thing that we'll come back to a little bit later on. Also, we say that work is directly related to a negative change in potential energy. Or in other words, work equals negative delta U. And we'll say a little bit more about this in just a second. An example of conservative force would be gravity or a spring force, or even electric and magnetic forces. Non-conservative, we say that the work is path dependent and the work along a closed path is not 0. So this is usually friction and then also magnets when we have motion involved. Okay. So, just to go back to our thoughts just a moment ago, with work being equal to negative change in potential, imagine that we have a system where there's no total change in energy. Total change in energy is 0. Well, energy, at least mechanical energy, is made up of potential and kinetic. So if we add, kinetic is K and potential is U, that's equal to 0, which means that delta K plus delta U is equal to 0. And we know that delta K is equal to negative delta U. But from the work energy theorem, delta K is also work. So we said a moment ago that potential energy is U, and this is a type of mechanical energy possessed by an object by virtue of its position or configuration. And people often say, oh, potential energy is like a rock that's about to fall because it has the potential to fall on you. So that's partially correct, but potential energy is a stored energy due to relative position of various objects. And whether it's mass or charge or other things, that's what potential energy really is. So it's the letter U. And here are a couple of different types: gravitational potential, UG, electrical potential, UE, which you'll see in the E&M half of the course, and spring potential, US. And we said this in the previous slide, the work done by conservative forces is the negative of the potential energy change. So work is equal to negative delta U. Okay, well, let's just take a second and talk for a moment about gravitational potential energy. We could say that the change in gravitational potential energy is the negative of the work done by the gravitational force on an object when it's moved. So work is equal to negative delta U. When you're near the Earth's surface, the gravitational pull is constant, so the force necessary is roughly equal to the weight. So this means that the change in potential energy is the negative of the work, which is equal to mgh. And what this means is that we have defined the point at which potential energy is equal to 0 to be the Earth's surface. Okay? And as long as we're near the Earth's surface, we can do this very easily. We'll see in a couple chapters that there's a better expression for gravitational potential energy where we don't want to do this, where we want to set a different value for the 0 point or a different location. But here's the thing, is that since work only depends on the change in potential energy, we really don't care about what the exact number is at any particular point. All we care about is the change as we go from one point to another. Okay, so we'll talk for a moment about spring potential energy. So springs obey Hooke's law, F equals negative kx. And we'll talk more about this when we do periodic motion and oscillation. But Fs is the restoring force exerted by the spring on an object. Okay, so if I have a block attached to a spring that was pulled to the right, the force that the spring will be giving is to the left. So that's how that works out. This means that the work is the integral of F dx, and this is the work done by the spring. So this means that the potential energy stored in the spring is simply 1/2 kx squared, and that's equal to the work done. And we do know where the 0 potential energy point is for a spring. This is where delta x is equal to 0. Okay, so here's an example. We're going to show later on that potential energy for gravity is really negative gmm over r. But what we want to do is we want to attempt to derive this, okay? And we want to get this from the universal law of gravity, which, by the way, we'll talk about this a little bit later on, but it's negative g m1 m2 over r squared. So don't worry if you haven't seen this before. We're just going to take this and show that it can turn into this potential energy function. So we have a couple of hints here. And the first hint is to use the fact that a small amount of work is going to be f of r dr. And we've seen this before when we did work. So that's going to be negative g m1 m2 over r squared dr. And we know that work is the integral of dw. So that means that the work that gravity does is the integral of negative g m1 m2 over r squared dr, which is going to give us g m1 m2 over r. Okay, so that's going to be the work done. And we can say, using our third hint, or our second hint rather, that delta U is equal to negative work, and that's a C for conservative. Okay, so that means that delta U is equal to negative G M1 M2 over R. And remember that delta U is U final minus U initial. And finally, we can say that because it's 0 when R is infinity, we could say that an initial value for this is 0. So this gives our potential energy due to gravity is equal to negative GMM over R. Okay, so next time we'll talk a little bit more about conservation of mechanical energy.